So for this example, I also want to illustrate the ability to solve equations using graphs. And that's something that we can use to solve any equation we want to. And one method to do that is to use intersection points. So I'm essentially saying that I want y to be the equation on the left, or the expression on the left, and y to be the expression on the right. So I'm going to call them y1 and y2. So then I know that the solutions correspond to the points of intersection. And it's the x coordinate that I'm worried about, right? Because I want the value of x so that the y's are the same. So here's the graphs in Desmos. Naturally, the 2 cosine squared is the green one, the wavy one, and y equals 1 is the horizontal one, the purple one. So we're just looking for where they intersect, and it looks like on 0 to 2 pi, and that's the interval that we're concerned with here, looks like there's 4 solutions. The odd pi is over 4, essentially. Because if I go further, notice that at 2 pi on the horizontal axis, I've hit all the solutions between 0 and 2 pi. The next one is after that, so we don't include that one. So the big question is, how do we get this result analytically? We know the answer. How do we get there analytically? So turning over to analytic techniques now, let's think about how you would solve an equation like 2y squared equals 1. You would first divide both sides by 2. And you'd have y squared equals a half, which means y is equal to plus or minus square root of a half, and then you'd rewrite it in a nicer form, and then you'd be done, right? Similar thing here, except we're going to isolate cosine x first, or cosine squared x, I should say. So we're still going to divide both sides by 2. So we have cosine squared x equals 1/2. And then remember, to get rid of the square, we take the square root of both sides. And whenever you take the square root of both sides, again, you need the plus and minus. So that means that cosine x is equal to plus or minus square root 1/2. Now, that doesn't look like a familiar ratio, but if we rewrite it a little bit here, we get 1 over root 2. And now that should look familiar because that's from your 45, 45, 90 triangle. Now, the intriguing thing about this problem is we want the ratio to be either positive or negative. Well, cosine is positive, and again, we should be thinking about a 45-degree angle here, right? Because that's the angle that gives you that ratio. We want either quadrant 1 or quadrant 4 at 45-degree angles. So this is where cosine is positive, but we also want where the cosine is negative, which means quadrant 2 and quadrant 3. So you're quickly seeing where these solutions are all coming from. The first solution is 45 degrees. The next solution is 135 degrees. The next, I don't want to use a similar color. The next solution after that looks like 225 degrees. And I'm just going to write down the last one because I think we see it. That's going to be 315 degrees going all the way around except for the last 45. So there, if we want to go to radians, this should look familiar. The answers are pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And there's our solutions solving analytically. Thanks for watching.